now we're going to turn our attention to logarithms. And as much as you don't like exponents, you probably dislike logarithms even more. But logarithms also, from a calculus point of view, are very nice. They have a very simple derivative rule. So for calculus problems, we actually don't mind logs at all. The best way to think about logarithms is as undoing exponentiation. So what I mean by that is if you have a log with a certain base and an exponential expression with the same base, then the log and the exponential function will sort of undo each other. They're inverses of each other. So for example, we saw before that 2 to the 5th was 32, so that means if we do the log base 2 of 32, we should get 5. In other words, the base here of 2 and the base here of 2 mean that the log will undo the exponent. So the log base 2 of 2 to the 5th will give you 5, it'll give you the exponent. Similarly, this guy is e cubed. If we wanted to get to that 3, the log base e is what I would want to use. And the log base e has a better name. Log base e is the thing that you would see referred to as natural log. Sometimes people say len or ln, but natural log is the same as log base e. And again, remember, e is not a variable. E is about 2.718. So what about properties of logs? Well, properties of logs are the same regardless of what base you use, just like exponent properties are. So in terms of natural log, one of our properties is this guy. Didn't mean to write through that. It's this guy. The log of a product is the sum of the logs. You can try this on your calculator if you want. If you pick any two numbers a and b and put these in, you'll find that this is actually correct. The explanation here tries to give you some idea of why that's true. So I would pause this and read through that if you'd like to see why that property works. And similarly, we have this property, again, that we can check using particular numbers. It's really very straightforward. When we say the log of 2 is 0.693, that means that 2 is e to the 0.693. So you can try that on your calculator and see that's about right. So instead of 2 to the 5th, we can say, well, 2 is really this guy. So 2 to the 5th is the same as this awful e expression to the 5th. But remember, our rules of exponents tell us that we should multiply the exponents. So 2 to the 5th is the same as e to the 5 times 0.0693. So that means that the natural log of this value is this exponent. So the natural log of 2 to the 5th is just 5 times log of 2. So in other words, the power that's inside there can be pulled out in front as multiplication. So let's see what this means graphically. Well, again, graphs of log functions and graphs of exponential functions are related to each other. These guys look just like the exponential function turned on their side. So if I drew the corresponding exponential, well, that's bad, exponential functions in here, they would look like this, where come down like that. So they're basically mirror images of these guys. So there's no reason that they have the same shape. If we investigated derivatives again, so I'll come back to my calculator and we'll do that. If we investigate derivatives again, if I use the natural log of x as my function, and again, just draw a graph. You see it over here. If I turn on my trace, not my trace, sorry, the calc, so second trace is my calc menu, and again, choose option 6, dy dx. If I pick an x coordinate, say 4, then the calculator tells me that my slope is 0.2005. Well, 0.25 is about 1/4, 1/4. So that's where this comes from. So when the x is 4, the slope is about 1/4. When x is 2, if you continue the investigation, you'll find the slope is about 1/2. When x is 10, the slope is 1/10. So what we find is that if our function is ln of x, then the derivative function should just be 1 over x. It's always 1 over, the slope on this curve is always 1 over its x-coordinate. So again, even though we don't really care for ln of x, maybe from an algebra point of view, from a calculus point of view, having the derivative just be 1 over x, that's a very simple formula, much simpler than for example, the derivative of the square root of x. And also, once again, we don't have to have base e. The natural log is certainly the easiest of all of these, just like the derivative of e to the x is the easiest of the exponential functions. But if we did have to do the derivative of log base 2 of x, well, it's really just the natural log of 2 over x. So there's a number here in the top that's calculated with a natural log instead of just 1. So when the base is e, we have 1 over x. When the base is something else, we have some number over x. But algebraically, that's no worse to work with than 1 over x.